up in the morning, gotta be fresh, gotta go downstairs, gotta have my bowl, gotta have cereal, seeing everything, the time is going, ticking on and on, everybody's rushing, gotta get down to the...
This video will have two parts. First, I'll give a brief overview of the different integration techniques that we've learned, and then I'll give a quick review of Stewart's advice for what integration techniques to try in what order, like what kind of general advice you might have for trying to compute integrals. So what are the integration techniques we know? The first one is U substitution. That's the only one that we talked about before midterm 1. And we saw that this works really well when you have an integral that involves a function together with the derivative of that function. Because then you can set the function to be equal to u, and the derivative is going to be part of the du, the derivative of the function together with the dx. So this worked really well to do integrals like natural log of x divided by x dx. Another place that U substitution worked really well is when you have the integral of an inner function and an outer function. If you have an expression like e to the cosine of x, often it's good to let u be equal to the inner function. In section 7.1, we talked about integration by parts. This is one of the most powerful integration techniques. It's good if your integral is given to you as a product of some things, because then you can think about different combinations, what to set equal to u and what to set equal to dv. And the whole idea is, instead of doing this difficult integral, the integral of u dv that you start with, what you get is an expression that is uv minus the integral of v du. So this is good if the integral of v du is simpler than the integral you started with. So the idea is you want to find a function u that gets simpler when you differentiate it. So like it's good if du is simpler than u. And then you want a function to be the part of dv, everything else, that doesn't get a lot worse when you take an antiderivative. So v shouldn't be a lot more complicated than dv. So for example, natural log of x is a function that gets simpler when you take a derivative. Like 1 over x is a simpler function than natural log of x. The next thing we talked about was section 7.2, these trig integrals. And we learned a process that will tell you in almost every case how to integrate a function that's like sine to the n times cosine to the m dx. So why do I say almost every case? Is there was one tricky case when both n and m are even. You should know how to integrate cosine squared x dx and sine squared x dx that use these identities where you rewrite that trig function, the square, in terms of cosine 2x. So here we needed to know a little more about trig identities than we have so far in the course. Similarly, we learned how to do, in almost every case, integrals like tangent to the n times secant to the m. And here, the difficult case is when one of these numbers is even and one of them is odd. We also do know how to integrate tangent and how to integrate secant. So you should know those, but you should not expect to see an integral like secant cubed x dx on an exam. That one is significantly harder. Okay, then we talked about trig substitutions, which worked really well for integrals of a very specific type, ones that had an expression like square root of a squared minus x squared, or square root of a squared plus x squared, or square root of x squared minus a squared. And in each of these cases, it suggests a different kind of substitution. In the first case, x equals a sine theta, then x equals a tan theta, then x equals a secant theta. And we saw examples of each one of these. Trig substitutions by definite integrals. When you do that substitution, you have to adjust the endpoints. The harder case is trig substitutions with indefinite integrals, because often you do this substitution, x as something like a sine theta, you get an antiderivative in terms of theta. And often the hard part is substituting back in terms of x. That sometimes involves the triangle method, where we write down a right triangle with its main angle being theta. And you have to be able to do things like, if you know the value of tangent of theta, how do you express sine of theta? And the last thing that we discussed, section 7.4, was integration using the method of partial fractions. And this is, we want to integrate rational functions, ratios of two polynomial functions. So the first thing is we talked about how to integrate your rational function when the rational function is proper, when the degree of p is less than the degree of q. When your rational function is not proper, in the last video of section 7.4, we talked about this extra step you have to do, this polynomial long division. So in all these problems, you have to factor the denominator q of x. And in all of the cases we'll see, q of x is either just going to have linear factors, possibly with repeats, or it could also have irreducible quadratic factors. We saw that the whole idea behind the method of partial fractions is we're going to take this rational function and write it as a sum of simpler rational functions. And the hard part here is often doing some algebra, how to find that partial fraction decomposition. You might have to do something like solve 2 equations in 2 variables or 3 equations in 3 variables that you get by putting everything over a common denominator. So I'll pause and erase, and then I'll go over Stewart's advice for how to think about how to attack integrals when you see one. In the rest of this video, I'll give a quick review of Stewart's advice for integration that comes on pages 504 and 505 of the textbook. The first thing to do is simplify the integrand if you can. The integrand is the function you're integrating. There are 2 nice examples here. If you have the square root of x times 1 plus square root of x, it's easier to just use the distributive law to expand that integral out. And then you have the integral of a sum, and it's just the sum of the integrals. So you can turn this integral into integral of square root of x plus the integral of x dx. And each of those pieces is pretty straightforward. Another example comes from trig functions. Sine of x plus cosine of x squared dx. I love examples like this. I always put something like this on the exam. If you just square it out, what you get is sine squared plus 2 sine times cosine plus cosine squared. And this sine squared plus cosine squared gives you a 1. So you get the integral of 1 dx plus 2 times the integral of sine of x times cosine of x. And this second one you can do easily with u substitution. The next piece of advice is to look for an obvious substitution. For example, if you have the integral of x over x squared minus 1 dx, you could do integration by partial fractions. It will work, but it is much easier to do this integral with a u substitution where u equals x squared minus 1. So du is 2x dx, and this integral simplifies really nicely. Stewart's next piece of advice is to classify the integral according to its form. If there's no obvious u substitution that will work, then look at this integral and think, what kind of integral is it? Like, what kind of function am I integrating? Do I have something with trig functions? Am I integrating a rational function? Do I have a product of a couple of things, which suggests maybe I'm going to do integration by parts? Do I have square roots? Do I have radicals in my expression, which suggests maybe trig substitution is the right thing to do? OK, maybe you try something and it doesn't quite work, or you try a simplification and it doesn't really work out. Stewart's 4th big piece of advice is try again. So if you don't have the answer after these first 3 steps, trying the most obvious thing, maybe you need to do something more complicated. Maybe there's some other u substitution to do. Or you could do integration by parts, even though maybe it's not an integral that you look at and immediately think, oh, let's try integration by parts. There's more advice like manipulate the integral. Maybe rewriting things in a clever way, like replacing a cosine squared x with a 1 minus sine squared x will help make the integral look simpler. So rather than go through every piece of this advice in detail, I would just encourage you to read Stewart's section 7.5 and check out the examples. And what I'll do in the rest of the videos for this lecture is just go through a bunch of examples of the kind of integral you might see on a midterm and talk through the process of how to decide which technique to use at different points.